Hey everyone, I'm McCabe Levingood, and today we are going to do Lab 4 for Physics 2211 on oscillations. We are going to begin with an introduction. The purpose of today's lab is to compare the predicted motion and the observed motion of the mass connected to the spring in both the x and y directions. We're going to plot the energy changes that are computed in the model. This includes the change in kinetic energy, gravitational potential energy, spring energy, and then the change in total energy. Today we're going to need a few physics principles and key terms. So starting off with Newton's second law, or the momentum principle, which states that the net force is equivalent to the change in momentum divided by the change in time. This explains how forces cause the momentum of a system to change over time. The energy principle states that energy can be neither created nor destroyed, but only change from one form to another. The change in energy of a system is equal to the work done on that system, plus the change in thermal energy between the surroundings and the system. And then finally, we have the spring force, which is the restoring force exerted by a spring when it is displaced from equilibrium. For today's lab, we're going to need some formulas. First, we have the velocity update formula and the position update formula, which are derived from Newton's second law. Then we also have Hooke's law, which is just the spring force. And then over to the right, we have a bunch of equations that are derived from the energy principle. So first, we have the energy principle itself, delta K, which is the change in kinetic energy. We have the change in gravitational potential energy near the Earth's surface, and then also universally. And then we have the change in electrical potential energy, which won't be used today, and the change in potential energy of a spring. Now we're getting into the experimental portion of the lab. So we analyze the motion of a spring and mass using tracker, and that's what's shown in the picture here. We have some graphs and then the data table of the position of the spring over a certain amount of time. Now we are moving on to the computational portion of the lab. We are going to use the values that we got from tracker and analyzing the motion of the spring, but that comes after we get all of the coding correct. So first of all, we have the initial conditions of the spring, and then we do the delta t, which is the time intervals. We set this on tracker. And moving over to the right, we have 9.8 meters per second squared, which is G. We have the spring constant and the relaxed length of the spring. This was all given in some of the pre-lecture videos. And then for the lines 88 through 90, we just have some equations. We have L, L hat, and S, which is the stretch of the spring. Okay, so now we're getting further into the code. Most of the code here are just the formulas that we discussed earlier. So we have the kinetic energy, gravitational potential energy, spring potential energy, and total energy. Again, we're just plugging in those formulas. We also have the gravitational force, the spring force, and the net force, which is all, again, just formulas. Then we have the velocity update formula, the position update formula, and we have the same values that we had earlier in the code with L, L hat, and the stretch of the spring. And then moving to the right, we're just plugging in those equations yet again to calculate the energy changes. So for changes in energy, it's K final minus K initial, for example. So it's the final energy minus the initial energy. Here are the results from the code. As you can see, we have the change in energy versus time, and then we also have the change in position versus time. To obtain these graphs, we added in the file with the data from the tracker analysis. Wrap up the lab, we're going to do a discussion. First, we're going to talk about if the energy principle was satisfied in the lab. So the energy principle was satisfied. The principle states that the total energy of a system remains the same unless acted upon by an outside force. In the lab, there is no surrounding force, so the energy should be preserved, and it was, as you saw in the graph. The values always canceled out to have a constant total energy. So as for example, as the potential energy increases, the kinetic energy of the system decreases, meaning the total energy of the system remains constant. And then using the data that we obtained in Tracker, we're making two separate estimates of the oscillation periods. So I have the two graphs from Tracker, and then we have the X period of oscillation, which is 1.425, and the Y period of oscillation, 1.519, and the difference is 0.094 seconds. Thank you so much for listening to my lab.